Right, so I'm going to take a step back here a little bit, and now that we've looked at some specific examples, we've got a good handle on what continuous looks like and what discontinuous looks like and why. I want to start approaching this a little generally again. And what I'm really looking to do, I want to make a statement about the continuity of the composition of two functions. And to do that, I need to make this little theorem first. Right, so look at what I'm saying here. First, remember, I'm talking about the composition of two functions. Now, you do see that down here in the final statement. Okay, but to start, I'm going to assume two things. I'm going to assume the limit of g of x, as x approaches the c, exists, and it equals L. And the second thing I'm going to do is I'm going to assume that f is continuous at that L. Okay, so what does all of this mean? Well, first, just notice this first. F is continuous at L. This means the limit as x approaches L of f of x equals f of L. That's just the definition of continuity. Okay, so let's see. What I'm going to do, I'm just going to write the definition. This is going to be an epsilon delta kind of proof. So I'm going to start by saying let epsilon be greater than 0. Then, playing off of that limit that I just wrote there, all I'm going to do is I'm going to quote the definition of the limit. Then, there exists delta greater than 0 such that the absolute value of f of u minus f of L is less than epsilon. I don't want to use x here, right? I'm going to use x on the next step when I'm actually talking about g, and that's the one I want to end up in my final statement about the limit of the composition. I need to use another variable here. So just in your head, think that u is standing in for x. Right, so this is true whenever the absolute value of, let's see, that's going to be u minus L is less than delta, and I'm going to make this delta 1, right? I'm going to use delta again in my next step when I'm actually talking about g and getting into the composition. So now I'm going to do this again, right? I'm going to apply the definition again, this time for this limit up here about g. All right, so I'm going to play off of that same epsilon. So for that epsilon, there exists delta greater than 0 such that the absolute value of g of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta. Okay, so far I haven't done anything really super creative. I mean, I've just quoted the definition twice. Right now, here comes the kind of cool step. Let u equal g of x. Right? Remember, g of x is what I'm substituting into f of x up here. Right? So these g of x's, they have to be in the domain of f. So if I do this, what I'm going to do is I'm going to go back to this inequality, and I'm going to substitute g of x into there. And this becomes the absolute value of f of g of x minus f of L is less than epsilon whenever the absolute value of x minus c is less than delta. And this is just the definition of a limit, right? This is saying, remember where the pieces come from, right? This is the x approaches part. So this is saying the limit as x approaches c, and this part here is the function and the final limit. So this is saying f of g of x approaches f of L. Excuse me, not approaches, equals f of L. And that's what I wanted to show, right? That was what I was trying to show. So these are the two statements that I was really driving at in the last section, and the last slide. Now I'm going to take a look at this at the second one first, right? This is saying if G is continuous at C, and F is continuous at G of C, then the composite function is continuous at C. All right, well, first, think about the last theorem. The limit as x approaches C of g of x equals g of c because g is continuous. And because f is continuous at g of c, I can apply my theorem. My theorem says the limit as x approaches c of f of g of x equals the limit equals f of the limit as x approaches c of g of x, but because g is continuous, this equals f of g of c. And that's what we needed to show to see that f of g of x is continuous at c. It's the definition of continuity at a point. So the first statement, now I know I jumped around. The first statement says another conclusion that, if you think about it, is something we'd kind of expect to be true. It says if a function is continuous on an interval and it has an inverse on that interval, then the inverse is also continuous. And this is a proof I'm going to leave as an exercise. We'll talk about it on the website. The thing about switching the roles of epsilon and delta, right? That's kind of how that proof is going to work. So I've got one more theorem for us to look at here. It's called the intermediate value theorem, right? And what this one says is if a function is continuous on a closed interval from a to b. So let me put that on my drawing. Let's put a over here, and I'm going to put b over here someplace, right? Then the function takes on every value between f of a and f of b. All right, so let's see. I need f of a and f of b. So if a is here, let's say f of a is here. So this is a comma f of a. And let's put b down here, right? And this will be b comma f of b. And what the theorem is saying is if you look at all of the numbers on the y-axis here between f of b and f of a, pick any number you like on that interval, and the function is there exists an x between a and b that equals that y value when you put it into the function. And you can kind of see this. It's kind of intuitive, I think. I'm going to pick a number here, right? I'm going to pick this value. Let's call it c. I'm saying that somewhere the graph of this function crosses this line. And to see that, try and draw so that it doesn't. Right? Try to draw a curve that goes from that starts at f of a, ends at f of b, doesn't cross that line, but is continuous. I think if you try, you'll see why continuity is so important here. Right? The continuity part of the theorem says you can't skip around. Right? If the function didn't have to be continuous, then I could draw something like this, and yeah, okay, it misses that point. But it's not. Because the function is continuous, for me to get from point f of a, down to point F of B. I can bounce around as much as I want in here, but eventually I'm going to have to cross that line, and there's my point, right? That X value gives me my chosen Y value. Okay, this theorem, it shows up from time to time, and it's just one of those little workhorse theorems that from time to time it's really helpful in drawing other conclusions. One real practical application of this, where we'll see this used, is in approximating the roots of functions. We're going to talk about that a little bit in an upcoming lecture when we talk about something called the midpoint method and Newton's method, right? If my function, sorry, I'm doing a lot of cleanup there. If my function is positive at A and negative at B, or the other way around, I know that the function has a root somewhere between A and B. Don't know where, right? I don't know where, but it's in there somewhere, because to get from here down to here, at some point, my function has to cross the x-axis, and that x value is going to be a root of the function. Okay, so that's the intermediate value theorem. So what's next? Well, this really brings us to the end of our discussion of limits. In the next chapter, we're going to start talking about something called the derivative of the function, and that's the point where we're really going to start getting to where we can answer specific questions, like the question we started off with back at the very beginning of the class about finding the instantaneous velocity of a moving object.